The moon has always looked silent, calm, almost harmless in the night sky. But returning to it may be far more dangerous than most people imagine. Beyond Earth's protection, astronauts face deep space radiation, brutal temperature extremes, toxic lunar dust, isolation, equipment failure, and a surface that can turn one small mistake into disaster. The moon is close enough to inspire confidence, yet hostile enough to punish it. Tonight, this journey moves step by step through the hidden dangers of going back. If space documentaries like this are your kind of escape, please like the video, subscribe to the channel, and join the next voyage into the dark. Far above weather, above cloud, above the blue air that holds oceans and birds and storms close to Earth, the path to the moon begins in a region that appears empty. From the ground, that emptiness can seem quiet and clean, like a dark field with a bright object hanging at its far edge. In practice, it is a long corridor of separation. It is a stretch of space so wide that the familiar habits of rescue, repair, and return begin to lose their meaning almost as soon as the spacecraft leaves low Earth orbit. The danger of going back to the moon begins here, in the simple fact that the moon is not close. It is near enough to remain in human imagination every night, yet far enough that a mission cannot depend on quick help once the journey is underway. The average distance from Earth to the moon is about 384,000 kilometers. That number is often repeated because it sounds manageable when spoken in one breath, yet distance in space is not felt as a number alone. It is felt as travel time, as narrowing options, as the growing delay between a problem and any outside response. A spacecraft on its way to the moon does not move through a region filled with stations, safe harbors, or nearby crews ready to meet it. Between Earth and the moon there is no chain of support. There's only the vehicle itself, the systems built into it, the training carried in human memory, and the supplies packed at launch. Every small failure has more room to grow there. Every repair must begin with whatever hands and tools are already on board. This is one of the main reasons a return to the moon may be more dangerous than it first appears. The moon is often discussed as the next step after low Earth orbit, as though it lies just beyond the doorstep of recent spaceflight. In a broad historical sense, that is true. The moon is closer than Mars, and missions there last far less time than an interplanetary expedition. But the difference between low Earth orbit and cislunar space is not a small extension. It is a change of environment, of logistics, and of consequence. Astronauts aboard the International Space Station circle Earth at a height where cargo vehicles can be sent. Emergency planning can rely on a return within hours, and communication remains nearly continuous. A mission heading toward the moon moves beyond that protected pattern. It enters a region where distance itself becomes a hazard. The spacecraft carries Earth away slowly in the windows. At first the planet still looks large, textured, and immediate. Continents, cloud bands, and the pale curve of the atmosphere remain visible. Soon Earth begins to shrink. That visual change has practical meaning as the spacecraft travels outward. The possibility of turning back remains, but return is no longer simple. Fuel is not unlimited. Trajectories are carefully chosen paths through moving gravity, not straight roads that allow free reversal at any time. A problem that begins on the outward leg must be judged against speed, remaining propellant, power use, oxygen use, water stores, and the condition of the crew. Even a wise decision may leave no easy outcome. The farther the spacecraft moves from Earth, the more every choice becomes a balance between imperfect options. Communication also begins to change in subtle ways. Radio signals travel at the speed of light, which is very fast, but not instant across lunar distance. A message from Earth to the Moon takes a little more than 1 second to arrive, and a reply takes a little more than 1 second to come back. This means a round trip in conversation takes more than 2 seconds. On Earth, this sounds minor in spacecraft operations, where timing, attention, and coordination matter. That pause alters the rhythm of support. A crew cannot rely on immediate verbal correction in the way a team in low Earth orbit often can. Control on Earth remains essential, but it becomes more distant in the most literal sense. The crew must solve more problems in place, with less direct guidance in the moment they unfold. The Moon is close enough for contact, but far enough to require a more independent kind of survival. Distance also changes the meaning of evacuation. In low Earth orbit, a medical emergency can lead to deorbit and landing on Earth within hours, on the way to the Moon, and later in lunar orbit or on the lunar surface. No such quick path exists. The journey back takes time, planning, and a working vehicle. A severe injury, a cardiac problem, a toxic exposure, or a failure of life support cannot be handled by calling for immediate recovery. The crew and spacecraft must remain functional long enough to bring the problem home. This greatly raises the value of prevention. It also raises the seriousness of events that might otherwise be considered manageable. A condition that would be urgent but survivable near Earth may become life-threatening when help is several days away. There is another feature of this outer region that adds quiet strain. Remoteness does not announce itself with noise or movement. Space between Earth and the Moon often looks calm. There is no weather in the ordinary sense, no visible traffic, no nearby landscape rushing past the windows. That stillness can hide the severity of the setting. A mechanical fault may begin silently inside a pump or valve. A navigation error may appear only as numbers drifting from plan. A leak may reveal itself through pressure change rather than sound. The crew lives inside a sealed island moving through a place that offers no forgiveness for broken boundaries. Outside the walls there is vacuum, a near-total absence of matter. Inside there must be pressure, temperature control, air circulation, clean water, electrical power, and stable guidance. The farther from Earth the spacecraft travels, the more completely these systems become the whole world of those inside. This outer stretch of travel also forces engineers and mission planners to confront a basic truth of exploration. The challenge is not only reaching a destination, the challenge is maintaining a habitable pocket of Earth conditions while moving through a region that contains almost none of them. Human bodies do not cross cislunar space because they are suited to it. They cross because machines create a temporary interior against it. Every wall, tank, wire, filter, and computer must keep performing over days of exposure and motion. Redundancy, which means having backup systems in case one fails, becomes central to survival. Yet backup adds mass, and mass makes launch harder and more expensive. This is one of the constant tensions in lunar return safety calls for layers, but spaceflight punishes weight. The journey begins, therefore, with compromise carefully measured against danger. In this way, the route to the Moon reveals the first and widest layer of risk. Before landing, before dust, before cold shadow or equipment wear, there is the open distance itself. It separates astronauts from fast rescue, stretches every supply line, slows every exchange with Earth, and turns the spacecraft into a lone moving habitat surrounded by vacuum. Returning to the Moon means returning to that distance, and accepting that the first danger is not hidden on the surface below. It is already present in the long dark space between worlds. Beyond most of Earth's magnetic shelter, the journey to the Moon passes through a region that looks no different to the eye from the space left behind. The dark remains dark. Sunlight still falls in sharp, hard lines. Earth still shines behind the spacecraft, though smaller now, and the moon grows only gradually ahead. Yet this outer region holds a danger that cannot be seen in the window. It moves through the body without light, colour, or sound. It passes through metal, plastic, water, and flesh. It leaves traces measured not by sight but by changes in cells, in electronics, and in the slow accumulation of damage. This is radiation, a word that means energy moving outward, often from unstable atoms or violent events on the Sun and beyond the solar system. In cislunar space, radiation becomes one of the most serious reasons that returning to the Moon is more dangerous than many people first imagine. On Earth, life develops beneath layers of protection. The atmosphere above absorbs much harmful incoming energy. The magnetic field around the planet, formed by motion within Earth's deep interior, bends many charged particles away from the surface. These protections are not perfect, but they are powerful. They reduce human exposure so completely that most people pass through daily life without noticing the storm of energetic particles that fills space beyond. Low Earth orbit still lies partly within this magnetic protection. Astronauts there receive more radiation than people on the ground, but they remain near Earth's shield. A spacecraft travelling to the Moon leaves much of that advantage behind. It enters a region where exposure rises because the natural barriers of Earth grow weak with distance. The radiation in deep space comes from more than one source. One part arrives steadily from the Sun, in the form of charged particles flowing outward through the solar system. Another part comes from far beyond the Sun, from energetic particles produced by distant violent events in the galaxy, such as exploding stars and other high-energy processes. These are often called galactic cosmic rays. The name sounds remote, and it is. They come from outside the solar system, cross immense distances, and enter spacecraft walls with energies high enough to make shielding difficult. A third source appears in bursts, when the Sun throws out clouds of energetic particles during solar eruptions. Those sudden events belong to a later layer of danger, but even without them, the background radiation in cislunar space is a constant condition of travel. This condition matters because human tissue is built from cells, and cells depend on long molecules, especially deoxyribonucleic acid, to store and copy the instructions of life. Radiation can strike atoms inside these molecules and break chemical bonds. Cells can repair some of this damage. Human biology is not helpless. Repair systems work constantly, correcting injury caused by normal chemistry as well as by outside exposure. But high-energy radiation can create complex damage that is harder to repair cleanly. Some cells die, some recover imperfectly, some survive with altered genetic material. Over time, this raises the long-term risk of cancer and may also affect the nervous system, the circulatory system, the eyes, and other organs. The exact degree of risk for lunar missions is still studied carefully, because exposure depends on timing, duration, spacecraft design, and solar conditions. Observations indicate that the hazard is real. It remains uncertain in some details how different forms of deep space radiation contribute to specific long-term outcomes in different individuals. Radiation also has a shorter timescale than cancer risk alone. At high enough dose over a short enough period, it can cause acute radiation sickness, a condition in which the body reacts to sudden heavy exposure. Symptoms can include nausea, weakness, and damage to blood-forming tissues and the digestive system. On a lunar mission, this kind of severe dose is most feared during major solar particle events. But the reason it matters even in the quieter background environment is that the margin for safety is already tighter than many spaceflight systems allow elsewhere. The crew cannot step outside the environment. They cannot call for rapid evacuation to a hospital. Medical treatment options remain limited to what travels with them. Radiation therefore becomes dangerous not only because of what it does biologically, but because of where the crew is when it happens. Shielding offers only a partial answer. This is another reason the danger is deeper than it first appears. It may seem natural to think that enough metal simply solves the problem. Some radiation can indeed be reduced by material between the source and the body. Water, fuel, food stores, and certain structural materials can help absorb part of the incoming energy. Spacecraft designers use careful arrangement of equipment and supplies to improve protection, and they may create a better shielded area for temporary refuge. But shielding against the highest energy particles is not straightforward. Very energetic cosmic rays can pass through substantial material. In some cases, when these particles strike shielding, they produce secondary particles, which create additional radiation inside the vehicle. More mass can help in some situations, but launch systems severely limit how much mass can be carried. Once again, safety meets the hard reality of spaceflight. Every kilogram added for protection must be launched, guided, and landed. The spacecraft's electronics face the same invisible environment. Computers, sensors, communication systems, and control hardware all depend on tiny organized patterns of charge and structure. Energetic particles can disrupt those patterns. A single particle may flip a bit in memory, confuse a sensor, or trigger a false command. Engineers guard against this with hardened components, error correction, and redundant architecture. Even so, radiation increases the chance that an ordinary operational day will contain something unexpected. For a lunar mission, that matters greatly. Human survival depends on machines that circulate air, regulate heat, track position, manage propulsion, and maintain contact with Earth. Radiation does not need to destroy a spacecraft dramatically to become dangerous. It only needs to disturb the wrong function at the wrong time. There is also a psychological feature to this danger. Humans are skilled at reacting to visible threats. Fire, smoke, collision, and falling pressure declare themselves in ways that command attention. Radiation often does not. The crew may know exposure is occurring because instruments record it, not because the body senses it. This creates a special kind of stress. The hazard is present, measurable, and serious, but often hidden from direct perception. The astronauts must trust instruments, procedures, and planning. They must live with the danger that enters the spacecraft despite the walls and despite careful engineering, because perfect exclusion is not possible. This makes deep space radiation one of the defining risks of returning to the Moon. It is not a dramatic surface obstacle. It is not a mountain, crater, or machine failure that can be photographed clearly. It is a property of the space between Earth and the Moon, a steady energetic environment that acts on flesh and electronics throughout the journey. Beyond most of Earth's protection, every hour of travel takes place inside that invisible field of exposure. The Moon may look close in the sky, but the path toward it leads through a region where the body carries the journey inward at the cellular scale, and where danger begins long before any landing leg touches the ground. Against the steady background of radiation, the space between Earth and the Moon also holds a more sudden form of danger. It begins at the Sun, the bright center of the solar system that makes life on Earth possible and, at times, makes travel beyond Earth far more hazardous. From a distance the Sun appears stable, a constant disk of light rising and setting by the order of planetary motion. In physical reality, it is a star made of hot plasma, which is gas so energetic that electrons separate from atomic nuclei. This plasma moves, twists, and carries magnetic fields that shift and tighten over time. Most of the time, these changes remain part of the ordinary activity of a living star. Sometimes they gather into violent releases of energy. When that happens, the danger for a lunar mission can rise quickly. One form of this solar violence is the solar flare, a burst of energy from the Sun's atmosphere. Another is the coronal mass ejection, a large eruption of magnetized plasma thrown outward into space. These events are related but not identical. A flare is mainly a sudden release of electromagnetic energy across a wide range of wavelengths. A coronal mass ejection is a moving cloud of solar material and magnetic field. Both can matter to astronauts, but for human health during travel to the Moon, the most feared consequence is often a rapid increase in energetic particles. These particles, mostly protons, can be accelerated to very high speeds and sent through interplanetary space. When such a burst reaches a spacecraft, exposure can rise sharply over a short period. This is why solar storm uncertainty becomes one of the most serious risks in lunar return. The danger is not only the strength of a storm, but the fact that the warning can be limited and the timing hard to manage. The Sun does not erupt at random in a complete sense. Its activity follows cycles and patterns shaped by its magnetic behavior. Scientists observe sunspots, magnetic regions, solar flares, and coronal mass ejections with increasing skill. Spacecraft and ground observatories watch the Sun continuously. Forecasting methods have improved. It is often possible to recognize periods when the Sun is more active and to identify regions on its surface that are more likely to produce eruptions. Yet prediction remains imperfect. The exact time when a magnetic structure on the Sun will release stored energy is still difficult to determine. Even when an eruption is observed, the speed, direction, and particle intensity that will matter to a crew in space are not always simple to predict in full detail. Observations indicate that warnings can be useful and often critical. It remains uncertain in many cases exactly how severe a particular event will become for a spacecraft on a specific path. This uncertainty matters because the Moon is not protected by a thick atmosphere or a global magnetic field like Earth's. A spacecraft on the way to the Moon also lacks Earth's broad shielding. If a strong solar particle event occurs, the crew cannot assume that ordinary spacecraft walls will be enough. The burst may unfold over hours, with particle intensity rising as the event develops. In some cases, the first signals reach instruments quickly, but the time available for action may still be narrow. The crew must move into the best shielded part of the vehicle, reduce exposure as much as possible, and wait. Mission control on Earth can help interpret data, but the spacecraft is far from immediate physical support. Safety depends on the design already in place, the supplies already stored, and the discipline of the crew. For this reason, lunar spacecraft may include a storm shelter, which is not a separate room in the ordinary sense but an area arranged to give better shielding during a solar event. Water containers, food packages, equipment, and structural materials may be positioned around it to absorb more incoming particles. This is a practical solution, but it is constrained by mass and volume. A spacecraft small enough to launch efficiently does not have unlimited space for thick shielding. The shelter may reduce exposure significantly without removing the hazard entirely. It may also be uncomfortable for long stays. If a storm lasts many hours, the crew may have to remain crowded in a confined area while watching power, air quality, temperature, and the continuing behavior of the event. The storm shelter is therefore not proof against danger. It is an admission that danger may arrive faster than the mission can escape it. The operational effect of solar storm uncertainty extends beyond biology. High-energy particles can disturb electronics, interfere with sensors, and complicate communication. Instruments that guide navigation and monitor spacecraft health may become noisier or less reliable in a strong event. Communication links can degrade, especially if the storm also disturbs space around Earth. This does not mean a lunar crew becomes instantly blind or silent during every solar event, but it does mean that the very period when clear data matters most may also be the period when the environment is least cooperative. The storm acts on both people and machines at once. It raises medical risk while also burdening the systems needed to respond well. Mission timing becomes a careful compromise for the same reason. A crewed mission to the Moon cannot eliminate solar risk simply by choosing a perfect launch day. Planners study the solar cycle and aim to reduce exposure where possible, but no launch occurs under a guarantee of calm. A mission may leave during a relatively quiet period and still encounter an unexpected eruption. The trip may be short compared with voyages to Mars, yet the danger remains real because a single large event can matter more than many days of modest background exposure. This is one of the unsettling truths of lunar travel. The total distance is finite, the destination familiar by name, the mission duration measured in days or weeks rather than years. And still the environment allows rare events that can dominate risk in a single episode. There is also a human factor in the way solar storms impose danger. They demand patience under uncertainty. The crew may know the sun is active. They may know that an event has occurred. They may know only that instruments show rising flux, which means the flow of particles through an area is increasing. Yet they may not know for some time whether the event will remain moderate or become severe. They must continue to perform procedure within incomplete knowledge on Earth. Many dangerous natural events still allow shelter within a wider society of roads, hospitals, and nearby assistance. In cislunar space, the spacecraft is the whole shelter. If the storm proves worse than expected, there is no second refuge to reach. This is why solar storms make the return to the Moon more dangerous than simple distance alone suggests. The journey outward already removes the crew from quick rescue and exposes them to the constant radiation of deep space. Solar storm uncertainty adds a sharper edge to that environment. It places a changing star at the center of mission risk and reminds planners that not all danger can be scheduled, predicted, or engineered away. The sun may appear serene from Earth, a bright fixed source above the days of human life, but along the road to the Moon it becomes a restless neighbor whose sudden outburst can test every layer of preparation. Beyond the uncertainty of solar storms, the journey to the Moon continues through an environment with another severe demand. It is not an explosion, a burst, or a collision. It is the ordinary thermal condition of open space, where heat and cold are governed less by surrounding air than by direct sunlight. Shadow, surface properties, and the slow movement of energy through material. On Earth, air and water soften temperature extremes. Wind carries heat away. Moisture absorbs it and releases it gradually. Clouds reflect sunlight. Ground and ocean store warmth and return it over time. In space between Earth and the Moon, those familiar buffers are absent. There is no air to spread warmth evenly over a spacecraft's outer skin. There is no breeze to cool a sunlit surface. There is no weather to moderate exposure. A vehicle in transit must manage sharp thermal contrasts largely by design alone. This makes thermal control one of the central hidden dangers of returning to the Moon. To understand why, it helps to begin with a simple point. Space itself is not cold in the ordinary earthly sense. Cold on Earth is often felt when moving air or contact with colder material draws heat out of the body. In the vacuum between Earth and the Moon, there is almost no matter to conduct heat in that way. Instead, thermal change depends mainly on radiation, which means the exchange of energy by electromagnetic waves and on conduction within the spacecraft structure itself. A surface in full sunlight can grow very hot because it absorbs incoming solar energy directly. A surface turned away from the sun can lose heat by radiating it outward into darkness. These two conditions can exist on different parts of the same vehicle at the same time. One side may be strongly heated while another cools rapidly. The problem is not merely high temperature or low temperature, but large uneven gradients across a structure that must remain mechanically stable and habitable. Sunlight in cislunar space is intense because there is no atmosphere to scatter or filter it. A spacecraft traveling toward the Moon receives strong direct solar energy on any exposed surface facing the Sun. Materials respond differently depending on color, finish, and composition. Some reflect much of the light. Some absorb more and warm quickly. Engineers therefore select coatings and external materials carefully, balancing thermal behavior with durability, weight, and other mission needs. But the outside of the spacecraft is only the first layer of the problem. Heat absorbed by outer surfaces must either be reflected away, stored briefly, or moved through the structure and released under control. If too much heat reaches the cabin or sensitive equipment, systems can drift beyond safe operating limits. Electronics, batteries, propellants, and life support hardware all function best within specific temperature ranges. Outside those ranges, performance can weaken or fail. Shadow creates the opposite challenge. When a surface rotates out of sunlight, it no longer receives the steady input of solar energy and begins to radiate heat away. In vacuum, a poorly controlled structure can cool faster than expected, especially at edges, exposed fittings, or thin materials. Some components become brittle in extreme cold. Lubricants can thicken or behave unpredictably. Batteries lose performance. Lines carrying fluids may face freezing risk if thermal management is inadequate. The spacecraft is therefore never simply heated or cooled as a whole. It is constantly balancing both. It must protect certain systems from overheating and others from excessive cooling, often at the same time and over short timescales as attitude, orientation, and exposure change. This balancing act becomes especially demanding because the crew also generates heat. Human bodies release warmth continuously. So do computers, pumps, lights, communications equipment, and chemical processes within the life support system in a closed spacecraft. Internal heat does not disappear on its own. On Earth, heat from a room can leak into the larger atmosphere through air exchange and convection. In space, it must be moved deliberately toward radiators, which are surfaces designed to release heat into the surrounding vacuum by radiation. These radiators must themselves remain exposed appropriately and must not absorb too much sunlight while trying to shed internal warmth. Their effectiveness depends on orientation, surface condition, and the total thermal load inside the vehicle. A spacecraft heading to the Moon is therefore a managed thermal machine at every moment, continuously shifting energy from where it is dangerous to where it can be safely released. The danger grows because thermal control is not a single device but a system of linked parts. Insulation limits unwanted heat flow. Heaters protect vulnerable components during cold periods. Pumps move fluid through loops that collect heat from equipment and carry it to radiators. Sensors monitor temperatures throughout the vehicle. Software and crew procedures adjust operation as external conditions change. If one part underperforms, strain can spread elsewhere. A pump fault can reduce cooling where electronics need it most. A damaged coating can change how much sunlight a surface absorbs. A sensor error can make a system respond too late or too strongly. This interconnectedness means that a thermal problem rarely remains isolated. In the confined environment of a lunar spacecraft, temperature control is woven into survival. There is also a geometric difficulty in transit. A spacecraft must orient itself for navigation, communication, power generation, and, at times, propulsion. The best position for one purpose may not be ideal for thermal balance. Solar arrays, if used, may need favorable angles toward the sun. Antennas may need alignment toward Earth. Thruster operations may require a different attitude. Each change alters which surfaces are lit and which remain shaded. Thermal engineers account for this in planning, but it means that temperature management is tied to the entire pattern of flight. Heat is not a background issue handled once and forgotten. It is part of navigation, power, crew, comfort, and equipment health all at once. For astronauts, the human experience of this thermal system remains mostly indirect when it is working well. The cabin stays within a narrow band of comfort. Air circulates. Surfaces feel stable. Equipment behaves as expected. That apparent normality can be misleading. It depends on constant correction against an external environment that is anything but mild. If thermal control begins to falter, the signs may emerge gradually at first. One area warms, another cools too much. Condensation forms where it should not, or a component draws more power to maintain temperature. Small imbalances can widen over time, especially during long exposure to sun or shadow. Because the spacecraft is days from Earth, the crew cannot rely on immediate replacement hardware or rescue. They must diagnose and adapt using the systems already aboard. Thermal extremes into lunar space therefore reveal another layer of why returning to the Moon is more dangerous than it may seem from the ground. The path is not merely dark and empty. It is an environment where sunlight can overheat exposed structures. Shadow can drain heat from critical parts, and the narrow comfort of life depends on carefully managed energy flow through every layer of the vehicle. A lunar spacecraft survives not by escaping heat and cold, but by holding them in balance moment after moment while crossing the long open distance between Earth and the Moon. As the spacecraft leaves the long transit behind and draws nearer to the Moon, the danger changes shape again. The risk is no longer defined mainly by the open distance between worlds, by invisible radiation, by solar uncertainty, or by the battle to keep heat and cold in balance during flight. It now gathers around motion in the Moon's gravitational field. At first, this may seem simpler than the journey outward. The destination is close. The vehicle is no longer crossing the broad space between Earth and Moon, but approaching the body it intends to circle. Yet lunar orbit is not a place of perfect ease. It is a region where precise motion matters deeply, and where the Moon's own internal structure makes orbital paths less simple than a smooth round world might suggest. Gravity is the force by which masses attract one another. Around a perfectly uniform body, this attraction would pull evenly according to distance from its center. An orbiting spacecraft would still need careful control, but the surrounding field would be relatively regular. The Moon is not uniform in that way. Its shape is close to spherical, but its interior is uneven. Some regions below the surface contain denser material than others. These variations create local changes in gravity. For a spacecraft in lunar orbit, this means that the pull beneath it does not remain exactly the same from place to place. Over time, These small differences can disturb an orbit, changing its height, shape, and orientation. These gravitational irregularities are often discussed through the idea of mass concentrations, sometimes shortened to mascons. A mass concentration is a region where more mass lies below the surface than a simpler model would expect. Many of these are associated with large impact basins that were later filled with dense volcanic material. The result is that the Moon's gravity field has hidden lumps, not visible to the eye from orbit, but measurable in the way spacecraft move above them. A vehicle passing over such a region can be pulled slightly more strongly than expected. One pass may produce only a tiny change. Repeated passes can build those changes into significant drift. This is why lunar orbit requires persistent attention. The path may appear smooth in a diagram, but in practice it is a continuous negotiation with an uneven gravitational landscape. This matters especially because some useful lunar orbits are naturally less stable than many people assume. A low orbit around the Moon can be attractive for observation, mapping, communication with surface teams, and preparation for landing. From a lower height, instruments see the surface in greater detail, and descent to the ground may become more efficient in some mission designs. Yet low lunar orbit can also be more vulnerable to disturbance from these uneven gravitational pulls. Without correction, an orbit that begins safely may change until the spacecraft passes too low over part of the Moon. In the most severe case, continued drift can lead toward impact. This does not happen instantly or without warning in a well-managed mission, but the risk is real enough that propulsive corrections are part of responsible planning. Fuel, therefore, becomes part of orbital safety in a direct way. Every correction burn uses propellant. Propellant is mass carried from Earth at great cost. It must be budgeted for insertion into orbit, for later maneuvers, for landing if landing is planned, for departure, and for contingencies. This means orbit is not only a geometric problem, it is a resource problem. A spacecraft cannot correct its path endlessly. Every unexpected change in orbit consumes some of the margin meant to protect later stages of the mission. If a vehicle must perform more correction than planned, the consequence may ripple through the entire mission design. Time in orbit, landing opportunities, surface operations, or return planning may all tighten as propellant reserves shrink. The Moon also rotates slowly, and its terrain varies sharply. Mountains, crater rims, and deep basins shape the meaning of altitude in practical terms. A spacecraft described as being in a low orbit is not equally far above every part of the surface below. Over high ground, the true clearance may be smaller. Over deep basins, it may be larger. Safe orbital planning therefore depends on detailed knowledge of topography as well as gravity. Modern missions benefit from far better mapping than earlier generations had, and this has greatly improved lunar navigation. Even so, exact knowledge does not remove the need for caution. It only allows caution to be applied more intelligently. The Moon remains a body whose surface and gravity together make close, orbital flight a matter of precision rather than routine. Another difficulty comes from the fact that lunar orbit is often part of a chain of events rather than an end in itself. A spacecraft may arrive carrying crew, hardware, and strict schedules. It may need to align with landing sites, lighting conditions, communication windows, and surface mission plans. Each of these goals may favor particular orbital characteristics, yet the safest and most stable orbit in one sense may not be the most useful in another. Mission planners therefore choose paths that balance operational value against orbital maintenance demands. The orbit must serve the mission while remaining controllable within the fuel and time available. This again reveals why a return to the Moon may be more dangerous than it first appears. Danger rarely comes from one dramatic flaw. More often, it comes from many reasonable demands pressing against each other at once. For the crew, orbital fragility has a special psychological quality. The spacecraft is no longer between Earth and Moon, but it is not yet resting on solid ground. Below lies a world close enough to see in great detail, marked by craters, ridges, and sharp shadows. The horizon curves swiftly beneath the vehicle. Features pass in silence. The moon seems near, but proximity does not mean security. The crew lives inside a path that remains valid only because motion, gravity, and correction stay in careful agreement. The orbit is not a fixed track suspended in space. It is an ongoing state created by speed and falling at once. If that balance shifts too far, the path changes with it. Communication and tracking help manage this. Ground teams on Earth and navigation systems aboard the spacecraft measure the orbit, compare it to prediction, and plan burns where needed. Modern models of the lunar gravity field are detailed and powerful, yet the need for such detail is itself evidence of the challenge. A simple gravitational environment would demand less constant refinement. Around the Moon, successful orbit depends on knowing invisible structure beneath the crust, understanding how that structure alters motion, and maintaining enough control authority to respond. The spacecraft must arrive with good data, reliable engines, accurate timing, and disciplined operations. A small misjudgment can remain small if caught early. Left unchecked, it can widen into a serious hazard. Lunar orbit, then, is not merely the calm waiting room before descent. It is its own dangerous region, shaped by the Moon's hidden unevenness and by the narrow margins of fuel and altitude that safe operations require. Returning to the Moon means returning not just to a distant destination, but to a gravitational field marked by buried structure and subtle instability. A spacecraft that circles there safely does so through constant precision, because the space above the Moon is governed not by smooth simplicity, but by a roughness written invisibly into the body below. From the fragile paths of lunar orbit, danger narrows into the final descent. The spacecraft no longer circles above the Moon as a moving balance between gravity and speed. It begins to give up that balance deliberately and move toward the surface. This stage may seem, from a distance, like a simple reduction of height, but in reality it is one of the most demanding moments in the entire mission. Landing on the Moon is not like landing through Earth's atmosphere. There is no thick air to slow the vehicle with wings or parachutes. There is no cushion of dense gas to absorb errors gradually. The descent depends almost entirely on engines, guidance, sensors, and the accurate reading of a surface that grows from distant pattern into immediate terrain. In this narrowing region, one of the great hazards of returning to the Moon becomes clear. Again, the surface does not wait quietly beneath the spacecraft. The act of landing changes the surface itself, especially through dust. The Moon is covered by regolith, a layer of broken material produced over immense spans of time by impacts. Regolith is not soil in the earthly sense, because it does not form through water, roots, microbes, and the long chemistry of living landscapes. It is dry, fragmented rock and mineral material, shaped by relentless impacts and temperature extremes. At the scale of descent, this matters because the uppermost layer can be loose and fine. When rocket exhaust from a landing vehicle strikes that layer, it does not simply press downward and remain still. It scours the ground, it lifts particles, accelerates them outward, and builds a moving cloud close to the surface. This is the beginning of one of the Moon's most practical landing dangers. On Earth, Air carries dust in visible plumes and also slows particles as they travel. On the Moon, there is almost no atmosphere to do that work. Exhaust gases expand differently in vacuum, and once dust grains are lifted by the plume, they can move fast and low across the surface without the familiar drag that air would provide. The result is a harsh spray of fine and small particles driven outward from the landing site. Some particles rise into a temporary cloud that reduces visibility beneath the spacecraft. Others skim across the ground like a sheet of abrasion. The effect depends on engine power, vehicle height, local surface texture, and descent profile. But the basic challenge is clear: the closer the vehicle comes to the ground, the more its own engines can obscure and disturb the very surface it needs to understand clearly. Visibility is one part of the danger. During the last moments of descent, the crew or onboard guidance system must judge altitude, rate of descent, attitude, and position relative to hazards on the surface. Large rocks, slopes, crater edges, and uneven ground can all threaten a safe landing. Yet the exhaust plume can throw up so much dust that the surface loses contrast. Shadows soften or vanish behind the moving veil. Fine texture disappears. Features once visible from higher altitude may blur as the spacecraft reaches the point where exact awareness matters most. This creates a troubling contradiction. The vehicle must come close to the surface to land, but coming close makes the surface harder to see. The Apollo missions offer direct evidence of this problem. Astronaut observations and mission records describe dust moving strongly during the final phase of landing. As the lunar module descended, the exhaust disturbed the surface and created a visual effect that complicated the reading of terrain. Modern engineers study those experiences closely, along with later robotic landings and experimental work, because future lunar missions may involve heavier vehicles than those used in Apollo. A heavier lander generally requires more thrust, and more thrust can produce stronger interaction with the surface. Observations indicate that larger future vehicles could create more severe dust plumes and greater surface erosion near touchdown. It remains uncertain in detail how this will vary across different landing designs and local surface conditions. The hazard is not limited to the landing vehicle itself. Dust accelerated by rocket exhaust can strike nearby hardware if a landing occurs near an existing base, instruments, power systems, or other spacecraft. Because lunar dust particles can be sharp and fast, they may damage exposed surfaces, scratch windows or sensors, coat radiators, and degrade seals or solar panels. This means that future lunar operations involving repeated landings near shared infrastructure face a compounding risk. Each arrival may disturb the local environment and threaten the equipment already there. In that sense, landing through dust is not just an isolated moment of danger. It can shape the design of landing pads, site spacing, traffic patterns, and the broader layout of a lunar outpost. The physics of descent also leaves little margin for hesitation. Since there is no atmosphere to provide passive braking, the engines must reduce speed precisely. Too little thrust and the vehicle descends too fast. Too much and fuel is wasted or the landing becomes unstable. Guidance systems combine inertial measurements, radar or laser altitude sensing, and surface relative navigation methods to estimate position and motion. These tools are powerful, but they operate in a real plume environment. Dust can interfere with optical sensing. Reflected signals near the surface can become more complex. Vibrations and engine dynamics must also be managed. The spacecraft is therefore making decisions in a zone that becomes harder to interpret as it nears completion. There is another subtle challenge in lunar descent. The Moon's horizon and lighting can be deceptive. Without atmosphere, light is stark. Sunlit ground can be brilliant while shadows remain deeply black. Near the surface, This already makes texture harder to judge. Add a growing dust sheet, and the landing scene can lose the familiar visual cues that pilots on Earth use instinctively. A slope may look flatter than it is. A boulder may disappear in glare or dust. The apparent motion of the ground can become difficult to read. Even advanced automation does not make these perceptual problems irrelevant, because automated systems must be trained, tested, and trusted in the same conditions. Human supervision, where present, still depends on interpretation under pressure. All of this happens while fuel continues to decrease. Descent is a countdown in the most physical sense. Every second of engine burn consumes propellant that cannot be replaced. If the chosen landing area proves unsafe late in the approach, diverting to another spot may be possible only within a narrowing envelope. That makes dust more dangerous still. It does not merely reduce visibility, it reduces visibility while time, fuel, and altitude all diminish together. The crew or computer must continue downward and decide with less certainty than the situation ideally demands. This region of danger, then, lies between orbit and surface contact, in the exhaust-filled space just above the Moon. Returning to the Moon means returning to a landing environment where the vehicle actively disturbs the terrain during the last and most delicate part of descent. The engines that make landing possible also lift the abrasive dust that can hide hazards, damage equipment, and turn the final meters into a confused moving cloud. The surface is close. But closeness does not simplify it. It sharpens the need for precision, because the Moon greets arriving spacecraft with a ground layer ready to rise against them. After the engines settle and the dust falls back toward the ground, the danger of the Moon does not become simpler. It changes again, this time into the visual character of the surface itself. The landing may be complete, the vehicle standing still, the long motion of descent ended. Yet the surrounding landscape remains difficult to read in ways that are unfamiliar to life on Earth. The Moon has no atmosphere thick enough to scatter sunlight across the sky. There is no blue dome above, no soft haze over distant ridges, no gentle filling of shadow with reflected light from air. Illumination arrives directly from the sun and strikes the land with stark clarity in some places and leaves other places in near total darkness. On the lunar surface, light and shadow do not blend gradually, they meet sharply. This sharp meeting creates one of the Moon's constant operational hazards, because human beings and machines rely on visual cues to judge shape, distance, slope, texture, and movement. On Earth, vision works within an environment shaped by air, even on a clear day. The atmosphere softens the landscape. Distant objects fade slightly through scattered light. Shadows hold detail because light bounces through air and reflects from many surfaces. The eye and brain grow up inside this pattern and learn to use it without conscious effort. The Moon removes much of that help. In direct sunlight, the ground can appear intensely bright, in shadow. Features may disappear into darkness with little intermediate tone. A rock at the edge of a shadow may stand out sharply on one side and vanish on the other. Small depressions can look flat if light strikes them from a poor angle. Slight slopes may appear steeper or shallower than they truly are. The problem is not lack of light alone. It is the severe contrast between illuminated ground and black shadow. This matters because surface work depends on accurate seeing. Astronauts stepping away from a lander must judge where to place their boots, how far a tool lies from reach, whether a ridge is easy to cross, whether a line or cable is twisted, whether a rock is stable under load, whether a route back to the vehicle remains clear, and whether the ground ahead contains subtle hazards, rovers, cameras, navigation systems, and mechanical arms face similar demands. If light behaved gently and predictably, these tasks would still require care. Under lunar lighting, care must be heightened because the eye is forced to move between extremes. It may adapt to brilliance and then immediately confront a region where detail is lost. It may adapt toward shadow and then be struck again by hard reflection from pale dust or bright sunlit metal. The moon's surface material contributes to this effect. Regolith reflects sunlight in a way that depends on angle, grain properties, and local texture. Some areas can appear almost washed out when the sun is high enough to reduce visible relief. When shadows are short, the surface may lose much of the contrast that normally reveals small bumps and hollows. This can make a landscape look smoother than it is. At other times, when the sun is lower over the horizon, small features cast long dark lines and relief becomes easier to see. But those same long shadows can hide their own interiors. A crater rim may stand out beautifully while the crater floor becomes unreadable. A boulder may be easy to notice, yet the ground beyond it may disappear into darkness. Good visibility on the moon is therefore not a fixed condition. It changes with solar angle, local topography, and the task being performed. Near the poles, where many future missions are interested in water ice and longer access to sunlight on certain high points, the lighting challenge can become even more severe. Because the sun stays low over the horizon there, some crater interiors remain in permanent shadow. Permanent shadow means regions that sunlight does not directly reach over very long timescales. These places are scientifically valuable because they may preserve ice and other volatiles, which are substances that can turn easily into gas, yet they are operationally difficult. Temperatures remain extremely low, and the visual environment is harsh. The edge between lit and unlit terrain may fall across broken ground, where a small mistake in movement or navigation has serious consequences. A region that appears close and manageable from one angle may conceal steepness or loose footing when approached. The lander itself adds to the visual challenge. Its surfaces may reflect strong sunlight. Equipment, antenna, ladders, and structures cast hard-edged shadows that shift with time. Dust on suits and visors changes reflectivity. Helmet visors must protect the eyes from intense brightness, while still allowing detail to be seen. This balance is not trivial. Too much glare reduction can make shadowed regions harder to interpret. Too little can strain vision and reduce contrast in bright zones. Apollo astronauts described the unusual difficulty of estimating distances and sizes on the moon, where the lack of atmospheric perspective altered familiar judgment. Objects could appear closer or farther than expected because the usual softening of distance was absent. Observations indicate that this effect can complicate surface movement and spatial awareness. It remains uncertain how much modern displays and training can fully compensate in every terrain and lighting condition. The hazard extends beyond human perception into automated systems. Cameras and navigation software depend on contrast, feature recognition, and stable illumination. A machine trained on one lighting geometry may perform less well in another. High dynamic range, which means a wide difference between darkest and brightest visible values in the same scene, is difficult for sensors as well as eyes. A camera may expose for the bright ground and lose shadow detail, or expose for shadow and wash out the sunlit surface. Image processing can help, but real-time operations still face limits imposed by optics, sensor capacity, dust on lenses, and computing choices. This is important for rovers, docking aids, hazard detection systems, and surface planning tools. The moon's lighting is not just visually dramatic, it is technically demanding. There is also a temporal dimension. The moon turns slowly, so a lunar day-night cycle is very long compared with Earth's. That means the motion of shadows across the ground is gradual, but it also means local lighting conditions can define operations for extended periods. A route that is manageable in one phase of illumination may become poor later as shadow deepens across a depression or glare rises from a low sun angle. Work schedules, traverses, instrument placement, and power strategies may all depend on this slow movement of light. The surface is not merely seen once and understood. It must be read again and again as the geometry changes. In this way, the moon presents a visible world that is harder to interpret than its quiet appearance suggests. Returning to the moon means working in a landscape where direct sunlight and profound darkness stand side by side, where distance can deceive, where texture can vanish in brilliance, and where shadow can hide real ground. The danger is not only that hazards exist on the surface, it is that the surface often reveals them incompletely. Under such light, each step, glance, and planned movement must account for a world that offers little visual forgiveness. Beneath the harsh light and shadow, the moon's surface reveals its next inward layer through touch, contact, and wear. What appears from a distance as pale, quiet ground is in fact a vast covering of broken mineral material laid down over immense spans of time. This covering is called regolith. The word refers to loose material resting above solid bedrock. On Earth, regolith may include soil shaped by water, wind, plants, microbes, and chemical weathering. On the moon, the meaning is different. There is no rain, no flowing water, no plant root, no burrowing life, and no thick atmosphere to round particles gently against one another. Lunar regolith forms mainly through countless impacts, from large collisions to tiny micrometeorites, breaking rock again and again into fragments of many sizes. Over time, this produces a surface layer that is dry, fragmented, and in many places extremely fine. Returning to the moon means returning to that layer. And one of the reasons this is more dangerous than it may seem is that lunar regolith is not merely dust to be brushed away. It is a persistent abrasive environment that invades systems, clings to surfaces, and turns routine contact into gradual damage. To understand this danger, it helps to begin with how the particles are made. When a meteoroid strikes the moon, there is no atmosphere to slow it much before impact. Even a small object can hit at very high speed. The energy released fractures rock, melts part of it, and throws debris outward. Over billions of years, this process repeats across the entire surface. Tiny impacts continue to chip, melt, and reshape exposed grains. Some fragments become glassy from melting and rapid cooling. Some grains are jagged because they have not been rounded by water or long transport in air. The result is a material that often behaves more like crushed, sharp mineral debris than like the soft household dust of Earth. This difference is central. Lunar dust is dangerous partly because it is not smooth. The fine fraction of this material is especially troublesome. Small particles can adhere to suits, boots, gloves, tools, cables, and vehicle surfaces. On the moon, electrostatic effects may also influence how dust behaves. Electrostatic means related to electric charge. Sunlight and plasma in the space environment can alter charge on exposed surfaces and particles, and this may contribute to dust attraction or movement under certain conditions. The exact behavior varies with local conditions and remains an active area of study. But the practical result is clear enough: lunar dust can be difficult to remove completely. It clings after contact. It travels inward on equipment. It settles into seams and interfaces. It becomes part of the operational environment almost as soon as surface activity begins. Apollo missions provide the most direct human experience of this. Astronaut reports describe dust-coating suits, darkening surfaces, reducing traction in some situations, and entering the cabin after moonwalks. Once inside, dust created smell and irritation and became a housekeeping problem in a small sealed volume. Observations indicate that lunar dust was abrasive enough to wear outer suit layers, scratch visors, and interfere with some mechanical components. It remains uncertain in full detail how future long-duration exposure will affect newer materials and systems under repeated use, but the basic lesson is well established. Dust on the moon is not a cosmetic nuisance. It is a system-level hazard. Its abrasiveness matters because many lunar systems depend on moving contact between parts. Suit joints flex, zippers or seal interfaces close and reopen, glove bearings rotate, tool latches engage, rover wheels turn, hinges, connectors, sample containers, and instrument covers all rely on surfaces meeting predictably. Introduce fine, sharp particles into those contact points, and friction increases. Surfaces may scratch. Seals may no longer mate cleanly. Lubrication becomes more difficult to manage. Wear accelerates. A single exposure may not cause failure, but repeated exposure can slowly change how a mechanism behaves. This means dust damage often accumulates quietly. The danger is not always dramatic in one moment. It grows through repetition, which makes it especially serious for extended lunar stays. The human body also meets this hazard directly. On the surface, astronauts remain protected by pressure suits and life support systems. Inside a habitat or cabin, however, any dust brought in becomes a possible inhalation concern. Very small particles can enter the respiratory tract if not controlled. Lunar dust chemistry and particle shape have raised concern because sharp fine particles may irritate lung tissue. During Apollo, astronauts reported temporary irritation of eyes, nose, and throat after exposure to dust inside the cabin. Scientists study these effects carefully, drawing partly on toxicology and partly on the limited human experience available. Observations indicate reason for caution, especially during longer missions with repeated exposure. It remains uncertain exactly how hazardous different particle sizes and compositions would be over months of habitation. This uncertainty does not reduce the seriousness of the issue. It increases the need for containment, filtration, and clean transition procedures. Dust also alters thermal behavior. A radiator, visor, optical sensor, solar panel, or reflective surface is designed with a certain response to light and heat. Coat it with dust, and that response changes. A radiator may reject heat less efficiently. A solar panel may receive less light. A camera window may lose clarity. A reflective surface may absorb more sunlight and warm more than intended. This matters because lunar missions depend on precise control of energy, temperature, and visibility. Dust therefore damages not only by scratching or clogging, but also by changing how hardware interacts with light and heat. A thin layer can be enough to matter if the system requires stable performance over many cycles. Movement across the surface keeps renewing contact with this material. Every footstep disturbs it. Every wheel grinds through it. Every tool set down and lifted again gathers some amount of it, because the moon has low gravity and no atmospheric cleaning process. Disturbed particles do not settle and disappear in the same way they would on Earth. tracks and disturbances can remain for long periods. Dust lifted during activity may fall back onto nearby equipment without any wind or rain to carry it away later. The environment therefore has a kind of memory. Each excursion leaves behind altered patches, coated surfaces, and transferred material that must be managed actively by the crew. This changes the design philosophy of lunar operations. On Earth, a person can often tolerate dirt and abrasion in the field because water, air, and easy replacement support recovery. On the Moon, prevention becomes more important than cleaning after the fact. Airlocks, suit ports, surface brushes, vacuum systems, filters, material coatings, and dust-tolerant mechanisms all become important not because engineers enjoy complexity, but because ordinary exposure can otherwise undermine mission survival over time. The more often crews go outside, the more critical these protections become. A successful lunar mission is therefore not only a matter of reaching the surface and performing tasks, it is also a matter of keeping the surface from gradually entering and degrading everything that supports life. In this inward layer of danger, the Moon shows its skin as an active adversary. The regolith underfoot is ancient, dry, broken, and sharp. It clings where it touches, wears what it enters, and follows astronauts and machines back from every excursion. Returning to the Moon means returning to a world whose ground is not passive terrain, but a persistent, abrasive material that works its way into seals, joints, optics, lungs, and thermal systems. The surface does not merely support human presence. It resists it grain by grain. Below the layer of dust and broken stone, the next inward region of danger is the human body moving through lunar gravity. At first glance, this seems like one of the Moon's gifts rather than one of its threats. Gravity at the lunar surface is about 1/6 of that on Earth. A person who feels heavy on Earth will feel light on the Moon. Large tools and equipment seem easier to lift. Steps can lengthen into bounding motion. Loads that would strain the body on Earth may appear far more manageable. This lighter condition helped make the Apollo surface excursions look energetic and almost playful in some moments. Yet the lower pull of the Moon carries hidden costs. It changes how muscles work, how bones bear force, how balance is maintained, how falls happen, and how fatigue develops through repeated activity. Returning to the Moon means returning to an environment where movement may look easier while becoming, in important ways, more dangerous. Human bodies are built under Earth gravity from birth onward. Muscles, bones, joints, and the inner ear develop within that constant pull. The inner ear, especially structures filled with fluid, helps the brain judge motion, head position, and balance. The eyes, the nerves in muscles and joints, and the pressure felt through the feet all work together to guide upright movement. This coordination is deeply practiced. On the Moon, the same systems still operate, but they must work in a different gravitational setting and often while enclosed in a pressure suit. The result is not simple freedom, it is adaptation under constraint. A step no longer behaves exactly as expected. A push sends the body farther. A stumble unfolds more slowly in one sense, yet may end in a wider and harder fall because the body travels differently before contact. The lower gravity reduces body weight, but it does not reduce mass. Mass is the quantity of matter in an object, and it determines resistance to changes in motion. On the Moon, an astronaut and a tool both weigh less, yet both still resist starting, stopping, and turning because their mass remains the same. This distinction is crucial. A large object may feel easy to lift, but once moving it still carries momentum. A person may begin a hop or stride with little effort, but stopping precisely can be awkward In a pressure suit, where joints resist bending and the center of body mass is altered by backpack systems, that awkwardness grows. The astronaut feels lighter, but not necessarily more agile. The moon reduces load while preserving inertia, and together these produce unfamiliar movement demands. Apollo experience showed this clearly. Astronauts used several forms of locomotion, including careful walking, loping, and two-footed hopping. These methods emerged because ordinary Earth walking was not always the most efficient or stable pattern in a bulky suit under 1/6 gravity. Observations indicate that astronauts could move effectively with practice, but also that falling was common enough to be taken seriously. Rising after a fall could be difficult, especially on uneven ground or near equipment. This matters because any fall on the moon occurs inside a suit that is itself a life support system. A fall is not merely a bruise risk, it may threaten the suit fabric, dust seals, helmet, visor, tools, or backpack hardware. Even a minor surface incident can become serious when survival depends on the integrity of what the astronaut is wearing. The body's deeper tissues also respond to reduced gravity over time. On Earth, bones continually remodel themselves, which means old tissue is broken down and new tissue is built. This process responds partly to mechanical loading. Muscles pulling against bones and bones supporting body weight help maintain density and strength. In low gravity, the loading is reduced. If this condition lasts long enough, bone can lose mineral content and become weaker. Muscles, especially those used for posture and locomotion, can also shrink and lose strength when they no longer work as hard against gravity. These effects are well documented in astronauts living in microgravity. The moon's gravity is not zero, so the response may differ in degree, but it does not fully remove the concern. Observations and modelling indicate that 1/6 gravity may still be insufficient to prevent significant musculoskeletal loss during long stays. It remains uncertain exactly how protective lunar gravity would be over many months without strong exercise countermeasures. This uncertainty matters because lunar missions increasingly imagine not brief visits alone, but repeated excursions and possibly extended habitation. A crew that spends days or weeks in transit, then lives and works on the moon, may arrive already altered by reduced loading during flight. Once on the surface, the body regains some gravitational cue, but not Earth's full one. Heavy exercise systems can help maintain strength and cardiovascular health, yet these require time, power, space, and reliable hardware. Even with exercise, the body may not remain unchanged. Returning to the moon may therefore mean asking astronauts to perform demanding fieldwork while their muscles, bones, and balance systems are already adapting in complex ways. Fatigue on the moon can also be deceptive. Because body weight is lower, a task may initially feel easier than expected. Carrying a tool, climbing a gentle rise, or repositioning equipment may seem less tiring in the first moment, but fatigue is not determined by weight alone. Pressure suits require force to bend, gloves resist finger motion, breathing may be harder during exertion. The body must constantly stabilize itself in an unfamiliar gravitational field. Each correction of posture, each recovery from a slip, and each effort to keep tools aligned adds hidden muscular work. Over time, this can become exhausting in a manner that is less obvious than on Earth. A crew member may not feel the warning in the same way until coordination begins to decline. On the moon, declining coordination increases fall risk, and a fall risk is also a suit risk. The lunar terrain amplifies these bodily challenges. The surface is uneven, with slopes, craters, ejector blocks, and loose regolith. A step onto a dusty incline may slip, a boot may sink slightly into soft material, A rock edge may tilt under load. In low gravity, a stumble may carry the body farther than expected before recovery is possible. Because the horizon is near and visual cues can be harsh under stark sunlight, balanced decisions may already be strained by uncertain depth perception. The body is therefore moving through a landscape where mechanical footing, suit design, gravity, and lighting all interact. None of these hazards acts alone. Their combination is what makes surface movement more dangerous than its apparent lightness suggests. There is also the question of emergency response. On Earth, an injured field worker may be lifted by others, transported quickly, and treated in a medical system close at hand. On the Moon, even a modest injury complicates everything. A twisted joint, strained muscle, or fracture inside a suit environment may make it difficult to return to the habitat or lander. Another astronaut may be able to help, but rescue effort itself becomes physically demanding in low gravity and bulky equipment. Carrying or dragging a suited person is not straightforward, especially over uneven ground. Thus, the body's vulnerability under lunar gravity is not merely an individual issue. It affects crew operations, timelines, and survival margins for everyone involved. In this inward region, the danger of the Moon enters the body's own mechanics. 1/6 gravity lightens weight but not mass, loosens the familiar bond between effort and motion, and slowly reshapes muscle, bone, and balance during longer exposure. Returning to the Moon means working in a place where movement can feel easy at first, and become hazardous through misjudged force, hidden fatigue, falls, and gradual physical change. The body does not simply arrive and perform there. It must negotiate a new gravitational rule with every step. Inside the moving body of the astronaut, the effects of low gravity continue to unfold. But the next inward layer of danger lies at the boundary between that body and the surrounding vacuum. This boundary is thin, artificial, and entirely necessary. It exists in the pressure suit during surface activity and in the walls of the habitat or spacecraft during rest and work inside. On the Moon, survival depends on maintaining a stable internal environment against a near-total absence of external pressure. The difference between inside and outside is extreme. Air presses outward from within, vacuum presses inward by offering no resistance at all. This contrast makes every seal, joint, panel, and interface part of a delicate barrier. Returning to the Moon means returning to a place where life depends on the continuous integrity of these pressure boundaries, and where even small failures can have serious consequences. Pressure is the force exerted by a fluid, such as air, over an area. On Earth, the atmosphere surrounds every person and object, pressing from all directions. The human body is adapted to this condition. Fluids within the body remain in balance with the surrounding pressure. Gases dissolve in blood and tissues according to that balance. In space and on the Moon, outside pressure is extremely low. If a human body were exposed directly to vacuum, gases within the body would expand. Liquids could begin to boil at normal body temperature, and rapid loss of breathable air would lead to loss of consciousness. This is why the pressure suit and the habitat are not optional equipment. They are the environment itself, replacing the atmosphere that Earth provides naturally. Maintaining this internal environment requires careful control. The pressure inside a suit or habitat is usually lower than Earth's sea level pressure, but high enough to support breathing and bodily function. Oxygen concentration, temperature, humidity, and airflow must all be regulated. Carbon dioxide must be removed continuously because it accumulates from breathing and can become harmful at elevated levels. These systems rely on pumps, filters, valves, and sensors, all of which must function reliably over time. A failure in any part of this chain can degrade the quality of the air or the stability of pressure. Because the Moon offers no external support, there is no margin for passive recovery. Every function must be actively maintained. Seals are the first line of defense in this environment. A seal is a barrier designed to prevent gas from escaping or entering where it should not. Seals appear in many forms, including flexible rings at joints, gaskets between panels, and interfaces where equipment connects. On the Moon, seals face a combination of stressors. Pressure difference pushes outward from within. Mechanical movement at joints flexes materials repeatedly. Temperature cycles cause expansion and contraction. Dust from the regolith can enter contact surfaces and disrupt clean closure. Over time, these factors can degrade a seal's performance. A seal does not need to fail completely to become dangerous. A small leak can slowly reduce pressure or allow contamination of the internal environment. Leak detection is therefore a critical activity. Instruments monitor pressure levels and rates of change. A stable system should show only minor variations. If pressure begins to drop faster than expected, the crew must locate the source and respond. Finding a leak can be difficult, especially if it is small and located in a complex structure. The crew may use listening devices, visual inspection, or diagnostic procedures to narrow the search in a suit. A leak is even more urgent because the volume is small and the environment directly surrounds the body. In a habitat, there may be more time, but the stakes remain high. The Moon's vacuum does not forgive delay. Gas lost to space is not recoverable. Structural integrity supports the work of seals. The walls of a habitat or spacecraft must resist internal pressure trying to expand them. Materials are chosen for strength, weight, and resistance to temperature and radiation. Over time, however, materials can change. Thermal cycling can create small stresses. Micrometeoroid impacts can damage outer layers. Repeated use of hatches and docking systems can wear contact points. The design accounts for these factors, but they remain part of the environment. A pressure boundary is not a static wall. It is a working system that experiences load, time, and wear together. Hatches and interfaces present particular challenges. A hatch is a door between regions, often between the interior and the vacuum outside or between compartments with different pressures. Each time a hatch is open and closed, seals must seat properly. Dust carried on suits or equipment can interfere with this seating. Careful cleaning procedures and design features aim to reduce contamination, but complete elimination is difficult in future missions with frequent surface excursions. The number of cycles increases. Each cycle is an opportunity for small changes to accumulate. Over many operations, the reliability of these interfaces becomes a central concern. The suit itself is a specialized pressure vessel shaped for movement. It must allow bending at joints while maintaining a sealed internal volume. Bearings, soft joints, and layered fabrics work together to provide mobility and protection. These elements are subject to wear, especially in the presence of abrasive dust. A suit leak during a surface activity is a direct threat to the astronaut. The design includes redundancy and monitoring, but response time remains limited. The astronaut must return to a safe environment before pressure loss becomes critical. This ties the integrity of the suit directly to planning for distance, duration, and task complexity on the surface. Inside the habitat, pressure boundaries also define the daily life of the crew. Airlocks manage the transition between internal pressure and external vacuum. An airlock is a small chamber that can be sealed from the habitat, depressurized to allow exit, and then repressurized for re-entry. This process conserves air but introduces its own cycle of stress. Valves must operate correctly. Pressure changes must be controlled to avoid rapid shifts that could harm equipment or people. Surfaces within the airlock must tolerate repeated exposure to dust and vacuum. The airlock becomes a point where the outer environment presses most directly against the inner system. The consequences of failure at this boundary are immediate and serious. A rapid depressurization, where pressure drops quickly, can lead to loss of breathable air and physical stress on the body. A slower leak may allow more time to respond, but still requires swift action to locate and repair the problem. Because the Moon is far from Earth, there is no external rescue that can arrive quickly to stabilize a failing habitat. The crew must depend on redundancy, emergency procedures, and the robustness of their systems. This reinforces a pattern seen in earlier regions of danger. Distance magnifies the importance of internal reliability. There is also a broader operational effect. Every activity must consider the pressure boundary. Moving equipment between inside and outside requires planning. Samples collected on the surface must be handled in ways that protect the internal environment. Maintenance tasks must account for the possibility of introducing leaks or contamination. Even simple actions, such as connecting a tool or opening a panel, become part of a larger system where pressure integrity is always at stake. The boundary is not just a wall, it is a constant condition shaping behavior. In this inward layer, the Moon reveals a fundamental truth of human spaceflight. Survival depends on a thin envelope of controlled conditions held against a vast external vacuum. Returning to the Moon means maintaining that envelope through seals that must remain clean and flexible, structures that must remain strong, and systems that must remain reliable under stress. The danger is not only that the outside is empty, it is that the inside must remain full, stable, and separate at all times, with no room for failure in the boundary between them. Within the protected boundary of the habitat, where pressure is held and air is kept breathable, the next inward layer of danger emerges through the management of energy, time, and darkness. On the Moon, the cycle of day and night is unlike that of Earth. A single rotation relative to the Sun takes about 29.5 Earth days. This means that one period of continuous daylight can last roughly 2 Earth weeks, followed by a night of similar length. During daylight, sunlight provides a steady source of energy and illumination. During night, the surface falls into prolonged darkness, and temperatures can drop to extremely low levels. Returning to the Moon means returning to a place where survival depends not only on enduring harsh conditions, but on sustaining life through a long absence of solar input. Power, therefore, becomes not just a resource, but a central vulnerability. Energy on the Moon is often gathered from sunlight using solar panels. These panels convert incoming light into electrical power, which can then run life support systems, scientific equipment, communication devices, and environmental controls. During the long lunar day, a well-placed system can collect significant energy, especially if positioned in regions that receive near-continuous sunlight, such as certain elevated areas near the poles. However, even in these favorable regions, sunlight is not guaranteed at all times. Terrain can cast shadows. The angle of the sun changes slowly but persistently. Dust can settle on panels and reduce efficiency. The generation of power is therefore a managed process, dependent on location, maintenance, and careful alignment. The challenge becomes more severe when night arrives. Without sunlight, solar panels produce no energy. The habitat and its systems must rely on stored power or alternative sources. Batteries can store energy collected during the day. but they have limits in capacity and efficiency. As energy is drawn during the night, the stored supply decreases. Every system running inside the habitat consumes power, including air circulation, temperature regulation, water processing, communication, and computing. Even if some systems are reduced or turned off to conserve energy, the basic needs of the crew cannot be paused. Oxygen must continue to circulate. Carbon dioxide must be removed. Temperature must remain within safe bounds. Water must be available and usable. The longer the night, the more critical the balance becomes between stored energy and ongoing demand. Temperature during the lunar night presents an additional strain on power systems. Without sunlight, surfaces radiate heat into space and cool significantly. The habitat, if not actively heated, would gradually lose its internal warmth. Heating systems must therefore operate continuously, drawing from the same stored energy needed for life support. Insulation can slow the rate of heat loss, but it cannot stop it entirely. The longer the night, the more heat must be supplied. This links temperature control directly to power availability. If energy runs low, heating may be reduced, which can in turn affect equipment and crew safety. Some mission designs consider alternative energy sources, such as nuclear systems, which can provide power independent of sunlight. These systems offer the advantage of continuous energy supply, but they introduce their own complexities, including mass, safety considerations, and long-term reliability. Regardless of the source, the central issue remains the same. The Moon requires a steady flow of energy to maintain a small, controlled environment against an external world that provides none. The absence of energy is not a minor inconvenience, it is a direct threat to survival. Power systems must also endure the same environmental challenges faced by other hardware. Dust can coat surfaces and reduce efficiency. Thermal cycles between day and night can stress materials and connections. Radiation can affect electronics. Mechanical wear may occur in moving parts, such as tracking systems that adjust panel orientation. Over time, these factors can degrade performance. A system that begins with a comfortable margin may lose some of that margin as components age. This gradual change must be anticipated and managed, because the margin is what protects the crew during unexpected events. The long duration of the lunar night also affects human rhythm and activity. On Earth, the daily cycle of light and darkness helps regulate sleep, alertness, and biological processes. On the Moon, the external cycle does not match human habit. Inside the habitat, artificial lighting can create a stable schedule, but the knowledge of the external environment remains. Outside, darkness persists for days without interruption. Surface activity becomes limited or impossible in many cases due to low light and extreme cold. The crew must adapt to a pattern where external work is clustered during daylight and internal tasks dominate during night. This shift is not merely logistical. It affects mental state, pacing of work, and the sense of time. There is also a risk associated with transitions between day and night. As the sun sets or rises slowly over the lunar horizon, temperatures change, shadows lengthen or shorten, and power conditions shift. Systems must adapt smoothly to these transitions. A failure in timing or coordination can lead to periods where power demand exceeds supply, or where thermal control struggles to keep up with changing conditions. These transition periods require careful planning and monitoring, because they combine the challenges of both light and darkness. Communication and navigation can also be affected by the long night, depending on location. Line-of-sight communication with Earth may vary. Equipment used for navigation or surface operations may rely on lighting conditions that are no longer present, while internal systems can compensate. The loss of natural illumination changes how the environment is perceived and managed. The moon's night is not simply a darker version of its day, it is a fundamentally different operational state. In this inward layer, danger is shaped by time and energy rather than by immediate physical threat. The moon demands that a habitat remain alive through extended darkness, using only what it has gathered and stored. Returning to the moon means returning to a place where the absence of sunlight is not brief, where cold deepens over many days, and where every system depends on a finite supply of power. The challenge is not only to endure the day, but to survive the night without loss of function, because in that long darkness, the margin between stability and failure can become very thin. Beyond the management of energy and the endurance of long darkness, the next inward layer of danger lies in the attempt to use the moon's own materials to support human life. Among these materials, water holds a central place. Water can sustain life directly, and it can also be separated into hydrogen and oxygen, which are useful for fuel and breathing systems. On the moon, water is not present as flowing liquid on the surface. Instead, it is believed to exist in the form of ice in certain regions, especially near the poles, where some areas remain in permanent shadow. These cold traps may preserve ice over very long timescales. The presence of such ice offers promise for future missions, but it also introduces complex challenges. Returning to the moon means working with resources that are difficult to locate, extract, and process under harsh conditions. The first difficulty is distribution. Ice on the moon is not spread evenly across the surface. It is thought to be concentrated in specific regions, often within craters that do not receive direct sunlight. These areas can be extremely cold, with temperatures far below those experienced in sunlit regions. Reaching them may require traversing uneven terrain under poor lighting conditions. Even identifying the exact location and concentration of ice can be challenging. Instruments can detect signs of hydrogen, which may indicate water, but interpreting these signals into usable deposits is not always straightforward. Observations indicate that ice exists in some form in these regions. It remains uncertain how pure, how accessible, and how continuous those deposits are at the scale needed for sustained human use. Once a potential source is identified, the next challenge is extraction. Ice mixed with regolith does not present itself as a clean, solid block. It may exist as small grains or thin coatings on particles. Extracting it may require digging, heating, or processing large volumes of material to obtain a relatively small amount of water. Each of these steps requires energy, equipment, and time. In a cold, dark environment, machinery must operate reliably despite low temperatures, dust exposure, and limited power. Excavation tools must handle abrasive material. Heating systems must provide enough energy to release water without wasting scarce power. The process must also prevent loss of water vapor into the vacuum, which would reduce efficiency. Transporting extracted material introduces further complexity. If water is collected in one location and needed in another, it must be moved across the surface. This may involve rovers or other vehicles, each subject to the same dust, terrain, and mechanical challenges described earlier. Alternatively, processing systems may be placed near the source, but this requires building and maintaining infrastructure in difficult environments. The choice between transporting raw material and processing in place depends on many factors, including energy availability, equipment durability, and mission design. Processing water into useful forms is another step with its own demands. Water must be purified if mixed with other darts, then stored in a way that prevents loss or contamination. If used for fuel or oxygen production, it must be split into hydrogen and oxygen through electrolysis, a process that requires electrical energy. The gases produced must then be stored, handled, and possibly liquefied, each step adding complexity. Storage systems must maintain appropriate temperatures and pressures, and must remain sealed against the vacuum outside. Any failure in this chain can reduce the availability of a critical resource. The chemical environment of the Moon adds subtle challenges as well. Without an atmosphere or liquid water cycling over the surface, chemical processes occur differently than on Earth. Materials may behave in ways that are less familiar. Reactions that rely on dissolved substances or fluid transport must be redesigned for dry conditions. Equipment must operate in vacuum, where heat transfer and material behavior differ. This means that processes developed on Earth cannot always be applied directly. They must be adapted, tested, and proven under lunar conditions, often with limited opportunity for repair or replacement. There is also uncertainty in scaling. Small experiments may demonstrate that water can be extracted and used, but scaling this to support a sustained human presence is a larger challenge. A crew requires a continuous supply of water for drinking, hygiene, food preparation, and system operation. Interruptions in supply can have immediate consequences. Therefore, any system relying on local resources must be reliable over long periods. Redundancy, which provides backup in case of failure, becomes important again, but it adds mass and complexity. Balancing these factors is part of the broader challenge of living off the lunar environment. The use of local resources is often seen as a way to reduce dependence on supplies from Earth. This is true in principle, but it does not remove risk, it shifts it. Instead of relying entirely on transported supplies, a mission depends on the successful operation of extraction and processing systems. If these systems fail, the crew may lose access to essential resources. In some cases, stored reserves can provide a buffer, but long-term sustainability depends on continuous function. The Moon offers materials, but it does not offer them freely or easily. Environmental impact is another consideration. Extracting and processing material can alter the local landscape. Dust may be disturbed and spread. Equipment may leave lasting marks. While this may not pose an immediate threat to survival, it can affect future operations, especially if multiple missions use the same area. Managing these effects requires planning and coordination, adding another layer of complexity to resource use. In this inward region, the danger of returning to the Moon is tied to the challenge of turning a harsh environment into a source of support. Water and other materials may exist, but they are locked within conditions that resist easy use. Extraction demands energy and durable machinery. Processing requires reliable systems. Transport adds logistical strain. Each step must succeed for the resource to become truly useful. The Moon offers potential, but it demands effort at every stage. The promise of local resources does not remove danger. It introduces a new form of it, where survival depends on transforming distant, frozen, and hidden mud into the essentials of life. Within the systems that extract, transport, and process lunar materials, and within the machines that support every movement across the surface, another inward layer of danger continues to build quietly over time. It is not a single event, nor a sudden failure, but a gradual wearing down of parts under constant exposure to dust, temperature change, and repeated use. On the Moon, machinery does not operate in a forgiving environment. It works in a setting where fine abrasive particles enter joints, where lubrication behaves differently, where thermal cycles strain materials, and where maintenance must be performed with limited tools and limited opportunity for replacement. Returning to the moon means returning to a place where machines must endure a combination of stresses that steadily push them toward degradation. Mechanical systems on Earth benefit from conditions that help limit wear. Air carries away some heat. Moisture can aid in certain lubrication regimes. Gravity provides predictable loading that engineers design around with long experience. On the Moon, these assumptions shift. In vacuum, conventional lubricants may evaporate, thicken, or break down differently than expected. Engineers use specialized materials and coatings designed for space, but these are not immune to wear. Moving parts still experience friction, and friction still produces heat and gradual material loss. Without an atmosphere, there is also no simple way to carry away fine debris generated by wear. Particles remain where they are produced or migrate into other parts of the system. Dust intrusion is one of the most persistent contributors to this process. As described earlier, lunar regolith consists of sharp, irregular particles that cling to surfaces and penetrate small gaps. When machinery operates, these particles can enter bearings, gears, and sliding interfaces. Once inside, they act as abrasives, increasing friction and accelerating wear. A joint that once moved smoothly may begin to resist motion. A bearing may develop uneven surfaces. A seal may lose its effectiveness. Over time, these small changes can accumulate into significant performance loss or failure. Because many lunar systems must operate repeatedly over extended periods, even a slow rate of degradation can become critical. Rovers provide a clear example of these challenges. A rover must travel across uneven terrain, carrying equipment and possibly crew. Its wheels or tracks interact directly with regolith, which can vary in firmness and texture. Each rotation of a wheel grinds against the surface, lifting dust and exposing mechanical components to abrasion. Suspension system must absorb shocks from rocks and slopes. Motors must deliver torque reliably despite changing resistance. Over time, dust can infiltrate motor housings, electrical connections, and moving joints. Thermal cycles can expand and contract materials, loosening connections or altering tolerances. Observations from past missions show that even well-designed rovers experience wear and require careful management to continue operating effectively. Stationary equipment faces its own version of this problem. Instruments, power systems, communication arrays, and processing units may not move across the surface, but they still experience dust deposition, temperature variation, and radiation exposure. Dust settling on radiators can reduce their ability to release heat. Dust on solar panels can lower energy production. Connectors and switches may become less reliable as particles accumulate. Thermal expansion and contraction over the long lunar day and night can stress joints and materials, leading to small cracks or shifts. These effects may not cause immediate failure, but they reduce the margin of safety over time. Maintenance on the Moon is inherently limited. On Earth, a failing component can often be replaced quickly with parts from a supply chain. Skilled technicians can access tools, workshops, and support systems. On the Moon, every spare part must be carried from Earth or manufactured locally with significant effort. The crew must perform maintenance in a constrained environment, often wearing suits that limit dexterity. Time spent on repair competes with time needed for exploration, science, and other mission tasks. This means that systems must be designed not only for performance, but for durability and ease of repair under difficult conditions. Redundancy again plays a role. Critical systems may have backups to ensure continued operation if one component fails. However, redundancy increases mass and complexity. Each additional part must be launched, integrated, and maintained. It also introduces more interfaces where dust and wear can act. The balance between having enough backup and keeping systems manageable is delicate. Too little redundancy increases risk of failure. Too much can create its own challenges in operation and maintenance. There is also a cumulative effect across different systems. Dust that enters one part of a machine may be carried into another during maintenance or operation. A rover that travels across a dusty area may bring particles back to a habitat or processing unit. Tools used in multiple contexts can transfer contamination. Over time, the entire operational environment becomes interconnected through these small transfers. Managing this requires procedures for cleaning, isolation, and careful handling. But complete separation is difficult to achieve. Thermal cycling contributes to mechanical wear in less obvious ways. As temperatures rise and fall over the lunar day and night, materials expand and contract. Different materials may expand at different rates, creating stress at interfaces. Repeated cycles can lead to fatigue, a process where materials gradually weaken under repeated loading. Small cracks can form and grow. Fasteners may loosen. Seals may lose elasticity. These changes can alter the behavior of systems that depend on precise alignment and tight tolerances. Electronics, while not mechanical in the same sense, are also affected by this environment. Connections can degrade. Solder joints can experience stress from thermal cycling. Dust can interfere with connectors. Radiation can cause gradual damage or sudden disruptions. The reliability of control systems, sensors, and communication equipment is therefore tied to the same broader pattern of environmental stress. In this inward layer, the danger of returning to the moon is expressed through time and use. Machines that begin their operation in perfect condition gradually change under the influence of dust, temperature, and repeated motion. Each small change may be manageable, but together they form a trend toward reduced performance and increased risk. The moon does not provide the conditions that allow machinery to remain stable with minimal care. Instead, it demands continuous attention, robust design, and acceptance that wear is an ongoing process. Returning to the moon means building systems that can endure this process and planning for the effort required to keep them functioning. It means recognizing that failure is not always sudden, but often the result of many small effects acting together. In a place where repair is difficult and replacement is limited, the slow invasion of dust and the steady accumulation of wear become central challenges. The machines that support life and exploration must survive not only the initial journey and landing, but the long, persistent pressure of an environment that erodes them step by step. Within the layered demands of machines, materials, and environment, the next inward region of danger settles into the human mind. The body moves through low gravity, works within pressure suits, and depends on machines that must continue to function without failure. Inside this structure of physical survival, the mind carries its own burden. It must remain steady, attentive, and resilient in a place that offers little variation, little external comfort, and constant awareness of risk. Returning to the moon means returning not only to a distant landscape, but to a condition of prolonged isolation, confinement, and responsibility that shapes thought and emotion as much as it shapes physical action. Isolation on the moon is not absolute in the sense of total separation from Earth. Communication remains possible, and the crew is supported by teams on the ground. Yet the psychological distance is real. Earth is visible in the sky, but it is far away. The crew cannot return quickly. They cannot step outside into a wider environment. Every activity takes place within a small group and a limited set of spaces. Over time, this can create a sense of separation that differs from isolation on Earth. On Earth, even in remote locations, there is usually a broader world nearby with the possibility of movement, change, and contact. On the Moon, the environment beyond the habitat is not only remote but hostile, and access to it is tightly controlled by suits and procedures. Confinement is another defining feature. The interior of a lunar habitat or spacecraft is necessarily limited in volume. Space must be used efficiently, and every object has a purpose. The crew lives and works in close proximity, sharing air, resources, and routines. Privacy is minimal. Personal space is constrained. Over time, this can affect mood, behavior, and interpersonal dynamics. Small irritations may become more significant when there is no easy way to step away. Cooperation and discipline are essential, but they must be sustained under conditions that do not naturally support variety or escape. The rhythm of life also changes. On Earth, daily cycles of light and darkness, weather, and social interaction provide natural variation. On the Moon, these patterns are altered or absent. The long lunar day and night create extended periods of similar conditions. Artificial lighting and schedules can simulate a daily cycle, but the external environment remains different. The crew must maintain a sense of time and routine through deliberate structure. Without this, the distinction between work and rest can blur, and the sense of progression through days can weaken. Work on the Moon carries a constant awareness of consequence. Every task, whether inside the habitat or on the surface, is connected to survival. A mistake in procedure, a lapse in attention, or a misjudgment in movement can have serious outcomes. This awareness can create a background level of stress. It is not always intense, but it is persistent. The mind must remain alert over long periods, managing both routine tasks and the potential for unexpected events. Fatigue, both physical and mental, can affect this vigilance. As fatigue grows, the risk of error increases, which in turn can raise stress further. Communication with Earth provides support, but it also introduces its own dynamics. Messages take time to travel, and conversations do not have the immediacy of face-to-face interaction. The crew may receive guidance, encouragement, and information, but the experience is still one of being physically distant. Emotional support must often be maintained within the crew itself. This places importance on group cohesion, mutual understanding, and the ability to manage conflict. Training can prepare astronauts for these conditions, but the reality of living them over time remains challenging. The environment outside the habitat offers little relief, unlike Earth, where stepping outside can provide a change of scenery, fresh air, and sensory variety. The lunar surface is visually striking but also repetitive in its own way. The landscape is dominated by rock, dust, and stark lighting. There are no living systems, no changing weather, no sound carried through air. The absence of familiar sensory input can affect perception and mood. Even though the view of Earth in the sky can be a source of connection, it also reinforces distance. Sleep is another area influenced by this environment. The absence of a natural day-night cycle and the demands of mission schedules can disrupt sleep patterns. Artificial lighting and structured routines aim to support regular rest, but stress, workload, and environmental factors can interfere. Poor sleep affects cognitive performance, reaction time, and emotional regulation. Over time, This can compound other psychological challenges. There is also the weight of responsibility. Each crew member knows that their actions affect not only themselves but the entire mission. Decisions must be made carefully, procedures must be followed precisely. This responsibility can be a source of motivation, but it can also contribute to pressure. The knowledge that errors can have serious consequences is always present, even during routine tasks. Despite these challenges, human beings are capable of adaptation. Training, selection, and support systems are designed to prepare astronauts for the psychological demands of spaceflight. Structured schedules, clear communication, shared goals, and mutual support within the crew can help maintain stability. Activities that provide mental engagement, such as scientific work, exercise, and communication with Earth, can support well-being. Observations from past missions indicate that crews can function effectively under these conditions, but they do so through effort and management rather than ease. In this inward region, the danger of returning to the Moon is not found in external forces alone, but in the sustained demand placed on the human mind. Isolation, confinement, altered rhythms, and constant awareness of risk create a psychological environment that must be navigated carefully. The Moon does not provide the variety and support that Earth offers naturally. It requires the crew to create stability within themselves and within their small community. Returning to the Moon means carrying not only equipment and supplies, but also the capacity to remain steady in a place where the mind must work as continuously as the machines that support it. At the innermost layer of this journey, after distance, radiation, light, dust, machinery, and the mind have all imposed their demands, the danger continues into the act of leaving the Moon and returning to Earth. Departure is not a simple reversal of arrival. It requires a sequence of events that must unfold with precision, under conditions shaped by everything that has already occurred. The spacecraft must rise from the surface, enter orbit, travel back across cislunar space, and finally pass through Earth's atmosphere. At each stage, the risks accumulated during the mission remain present. Returning to the Moon means accepting that the final phase is not a release from danger, but a continuation of it in a different form. The ascent from the lunar surface begins within the same environment that challenged the landing. Dust may again be lifted by engine exhaust, obscuring visibility and interacting with nearby equipment. The vehicle must ignite its engines reliably after exposure to dust, temperature extremes, and mechanical wear during surface operations. Fuel must flow correctly. Valves must open as intended. Guidance systems must determine position and trajectory accurately, unlike Earth, where multiple launch facilities and extensive support exist. A lunar ascent vehicle operates in isolation. There is no external infrastructure to assist if something fails at the moment of ignition. Once the vehicle rises, it must achieve a stable orbit around the Moon. This requires precise control of thrust and direction. Errors in timing or orientation can lead to an orbit that is too low, too high, or misaligned with planned trajectories. The gravitational irregularities described earlier still influence motion. The spacecraft must navigate this environment while managing limited fuel reserves. The ascent stage is designed with these constraints in mind. But the margin for correction is not unlimited. A successful ascent is therefore a continuation of careful balance between propulsion, navigation, and resource management. After reaching orbit, the spacecraft may need to rendezvous with another vehicle or prepare for departure directly. Rendezvous involves matching position and velocity with another object in orbit, a process that demands precise timing and control. Even small errors can complicate the approach. communication delays with Earth remain present, requiring the crew to act with a degree of independence. The systems involved must function reliably, and the crew must execute procedures accurately under conditions that may include fatigue and accumulated stress from earlier mission phases. The journey back to Earth retraces the path through cislunar space, bringing with it the same exposure to radiation and thermal extremes. The duration of this return may be shorter than the outward journey, but it is not free from risk. Solar activity can still change. Radiation continues to act on both the crew and the spacecraft. Thermal control systems must remain effective. The integrity of pressure boundaries must be maintained. Any wear or degradation that occurred during the mission does not disappear. It travels with the spacecraft, influencing its performance during the return. As the spacecraft approaches Earth, a new environment emerges. Unlike the Moon, Earth has a dense atmosphere. Re-entry into this atmosphere is a controlled descent that converts the spacecraft's high speed into heat. As the vehicle enters the upper layers of the atmosphere, friction with air molecules generates intense thermal energy. This heat must be managed by a heat shield, a protective layer designed to absorb and dissipate the energy without allowing it to reach the interior. The effectiveness of this shield depends on its condition. Any damage or degradation sustained during the mission could affect its performance. The heat of re-entry is not a gradual warming. It is a rapid and extreme process that demands full reliability of the protective system. The forces experienced during re-entry also differ from those on the Moon. As the spacecraft slows, it undergoes deceleration, producing forces that act on the crew. After time spent in reduced gravity, the body must readjust to higher forces. This transition can affect circulation, balance, and overall physical response. Astronauts may experience changes in blood distribution and coordination. These effects are generally anticipated and managed, but they remain part of the challenge of returning from a different gravitational environment. Parachutes or other landing systems then bring the spacecraft to Earth's surface or to the ocean. These systems must deploy correctly and function as intended. Weather conditions, which are absent on the Moon, now become relevant. Wind, waves, and visibility can influence the final stage of landing and recovery. Coordination with recovery teams must be precise. Although Earth provides a supportive environment compared to the Moon, the final moments of return still require careful execution. After landing, the effects of the mission continue within the human body. Exposure to radiation, changes in gravity, and the demands of the mission may have altered physical condition. Muscles and bones may need time to recover. The immune system and other physiological processes may show changes. Medical evaluation and rehabilitation become part of the return. Observations indicate that astronauts can recover from these effects, but the process takes time and varies among individuals. It remains uncertain how repeated or longer missions might influence long-term health outcomes. The spacecraft itself also carries the marks of the journey. Dust may be present in compartments. Systems may show wear. Data collected during the mission must be analyzed to understand performance and identify any issues. This information informs future missions, contributing to the gradual improvement of design and procedure. The return is therefore not only the end of one mission, but part of a continuous process of learning and adaptation. In this final inward layer, the danger of returning to the Moon extends through the act of coming home. Each phase of departure, travel, and re-entry carries its own demands, shaped by the conditions encountered throughout the mission. The Moon does not release its visitors easily. It requires that they leave with the same precision and resilience that brought them there. Returning to the Moon means accepting that the journey does not end at the surface. and that the path back to Earth is a continuation of the same careful balance between human capability and an environment that offers no margin for error. The long path from Earth to the Moon and back unfolds as a series of environments, each with its own quiet demands. Distance stretches the meaning of help. Radiation moves unseen through matter and time. The sun, steady in appearance, carries the possibility of sudden change. Heat and cold trade places across the skin of a spacecraft. Orbit requires constant correction above a world shaped unevenly within. Descent stirs dust that hides the ground it rises from. Light sharpens into extremes that confuse the eye. The surface itself clings and wears, grain by grain. Gravity lightens weight while preserving mass, altering movement in subtle ways. Thin walls hold air against emptiness. Power must endure through long darkness. Resources lie hidden and difficult to use. Machines age under stress. The mind carries the weight of isolation. The return gathers all of these into a final passage home. In this steady sequence, the Moon appears neither welcoming nor hostile in a simple sense. It is a place that remains itself, unchanged by human expectation. Its dangers are not dramatic in isolation. They are persistent, cumulative, and interwoven. Each layer meets the next, forming a chain that must hold without failure from beginning to end. The journey succeeds when every part remains in balance long enough for the whole to be completed. Returning to the Moon therefore becomes an act of sustained care. It asks for attention to detail across distance, matter, energy, and human thought. It asks for systems that endure and for people who can remain steady within them. The Moon waits without urgency, its surface unchanged by the passing of years. Those who travel there must bring with them everything needed to live, work, and return, holding a small, stable world within a larger silent one.